Good morning, everybody. Thank you very much for coming back. So we've had the question to what's the, you didn't quite put it this way, but what's the status of the labels on names? So on the one hand, I told you that names are identified for equality on the atomic identifiers. So that suggests that the labels are irrelevant, which they are to equality and to ordering. On the other hand, I provided the facility to deal with labeled atoms, so why did I do that? So if we think, I'll jump into here now. If we think about a system F term, right, so my answer was really, if you want to see the engineering reasons, look in this file, the system F file. Changed it, have I? No, I haven't. Okay. But if we think about a typical type lambda term, so lambda A of type T, and then we do some stuff, and then we see an A and it's applied to a B. And maybe somewhere up here we have a lambda B of type T, and I'll make this be a lambda A of type S. So this is a very common schema, okay? We have some type information up here, and somewhere else we have two elements that interact, and now we want to decide whether we're going to accept what we're going to do with this. Now, mathematically, the answer is simple. All you need to do is to travel up to your typing context and look up A and B, and we see that A has type S and B has type T. Let's give this type S arrow, let's get T arrow T prime. So here we could say in satisfaction, yeah, okay, I'm going to accept A applied to B. Arjun, are you with me so far?
Yes, that sounds reasonable.
Yeah, and this is all completely standard and it looks totally innocuous. We've all seen this lots of times before. But if you think about the mechanics of it, we are here, and then we have to go to a context to look up information about A and B, and then we have to go back to here. Now, that's actually not so innocuous because that demands that we maintain a typing context. And I know we're very familiar with maintaining these typing contexts, but wouldn't it be nice if we could just look at A and B and just say, actually, I'm going to accept A and B because the information is right here, bang, right here, about whether to accept A applied to B. So wouldn't it be nice if the atomic identifiers A and B actually carried with them a label? That would make the typing algorithms easier because now all the information is local. So I'm torn between the desire to identify this entity here with the ID A and to tag it with semantic information, which will allow me to write my algorithms without having to maintain a global context. A little bit of cultural background. Part of the point of nominal techniques was to allow us to program on name-like entities without having to maintain a global context of bound names or of known names. So I didn't want to create a system that in principle allows you to do that, but in practice, anytime you want to do something useful with an identifier beyond look at it, like for example, associate some semantic information with it, like a type, I don't then want to force the programmer to have to maintain a global context of semantic information unless the programmer wants to. So I created names. And we see this design. Sorry, are you with me so far?
I think so. Yeah. So here you're using labels specifically for information that is not a name, morally or otherwise.
So just a bit of terminology. An atom is an atomic ID. A name is a labeled atom. So a name is something that associates information to an identifier, to an atom. That information is I'll say always, always going to be some kind of additional semantic style thing, even if it's just a display name.
Right, but so what I was mostly wondering is, let's say that we parse a lambda term using
Say
name.
that question, please. Supposing we what?
We parse a lambda term.
Yes.
Using the raw names from the raw program as labels. And now we start.
No, sorry, hang on. When you say name there, do you mean, what do you mean by name?
The raw things that we found in the program. So we wrote lambda x, lambda y, something.
Don't call them names, because that has a specific technical meaning in the context of this package. Call it something else, please, like a label, perhaps.
Okay, raw labels. And we use those as labels in the representation in Haskell.
Yep.
Now, suppose that we start manipulating this term using your nominal package. And then we print back the lambda term after the transformation using only the labels that we found. Is that the printed lambda term guaranteed to be well bound? Or could I have messed up something? Because I only used the labels and not the identifiers in printing.
I actually don't. Oh, I see. I see. So that depends on the program you've written.
So, but I can write transformations using your nominal package that would output a lambda term that is not well bound. So if I want to output a lambda term that's well bound, I should take into account the identifiers.
The short answer is yes, but I think in a rather trivial sense, it's like saying, so I can write a program that is not multiplication on the integers. Atoms and names are just data. You can do anything you want with this data.
Right, yes.
Let me carry on. You're asking good questions. Perhaps the intro that I have planned for this talk, it does touch on points related to what you're saying. But I will emphasize here, the slogan of this package is names are data. And you can do anything you want with this data, including swapping it and abstract it, but the program is free to do, quote, bad things. And what constitutes a bad thing? I don't think that can be statically type checked. It depends on what you want to accomplish. Thank you very much.
Thank you.
I will continue. So I'm going to go here and let us set up. So stat GHCI nominal. Here we go. And we're in. And now I'm just going to copy this little setup script over. Bang. There we are. So now I've just imported a bunch of stuff and we are set up. And now I will recreate my little environment here. So I'll just read through that just to remind ourselves of what this does. We created, you know this already, but I'll just say it again. We created a list of labels, which are trivial. That's interesting, the display's a bit odd there. Do I have atom list? Yes, I do. Okay, so I created myself a list of atoms, one for each label, and a list of names. Let's test that. Yep, looking good. And, oh, sorry, a list of trivially labeled names, MA, and I also created a list of usefully labeled names. And so now we're golden and we can carry on. Hands up if I can carry on to the next bit, please. Loving it. Thank you very much, guys. Okay, so I'm just going to recap the last lecture. We have seen atoms and names, and we've just discussed the differences between them. An atom is an atomic identifier. A name is an ID labeled with some label. I think of these as object level type annotations, and my model here is this. So the S here, this is a name. That's an atom. Whoops, try again. No, that didn't work. Okay, that was a name, that's an atom, that A is an atom, and that S is a label. We're fine so far. Name equality and ordering is inherited from the atomic IDs. Labels are ignored. Recall that we have swapping. Every type is in principle swappable, but you might, and there's a generic machine that will implement swappability, but you do need to tell Haskell to switch this machine on for the particular type. So this looks like a typecast constraint, but operationally it's saying switch the swapping machine on for the type A. Any questions so far? Jules, yes. Jules, please ask your question. You don't have a question, do you? Just left your hand up. Okay. So let's just look at this thing here. This is part of the generic machine, and somewhere in the names theory file, there is a line that actually says that if a swapping hits an abstraction, then it distributes down into the name and into the body. Don't worry about it, Jules. I could have done it myself. Okay, so please look at this carefully. If you have any questions, ask them now, please. Cool. Hands up if you'd just like me to run this program on some example input to see what it does. Okay, perfect. Thank you very much. So let's try swapping A and B. Well, let's just look at abst A. Now I need a name, don't I? Abst MA in MA MB. There we are. So MB is N2, displays as M2. MA displays as N1. The reason we've got a 5 here is because the abstraction bound A, and then when I wrote this in the interactive prompt, a show was invoked to actually output it to terminal, and the show, hang on a second, I'll tell you in a minute, Hussein, and the show created a fresh name for the bound atomic and MA just for the purposes of display. Now Hussein has asked, what are those square brackets? That's the list former. I abstracted MA in a list, MAMB. Let's look at the type. There you are. Okay. Does that answer your question, Hussein? Good, thank you. Now I will try to swap A and B in this abstraction. And what I'm predicting is that this B will get turned into an A, and this bound name will not be touched. It'll probably turn up as a 7 here, I reckon. It seems to be counting up in 2s. Yeah. You see here? So that's the MB turning into MA. And if I try to swap A and C, you see this is the MB left alone, and we just created another fresh name for the bound atom, so the swapping has not affected the binding at all. And I'm going to emphasize that this is part of the generic machine, so you never have to write this out. It happens auto-magically. If you create an inductive or any other data type and use the abstraction type off the shelf, then this will happen whether you like it or not. You use the abstraction, so in doing so, this is the behavior you demanded. Any questions so far? David, yes.
Hi, can you hear me okay?
No, not really.
Oh, right. One moment, I'll type it in the chat.
Okay. David, I'm going to carry on till you get your mix sorted out. But do not hesitate to put your hand up again. We have abstraction and concretion. There you are. And they have really weird types, which I will explain later. Abstraction is total, so this always makes sense. This always makes sense, but concretion is morally partial, but implemented as a total function. And we had a long debate about whether this was desirable. I consider this a feature, not a bug, right? So I consciously do not handle name hygiene in the Haskell type system. I think trying to do so would be a mistake. And this is following the slogan as before that names are data. If the programmer wants to put data together in strange ways in the privacy of their own home, it's not for me to comment on. Now I'd like to show you something a little weird that can happen. Guys, are you ready to see something a little weird? Hand up if you are. Excellent. I like the attitude. Okay, David has asked a question. David has asked, what is the meaning of swapping the abstracted variable? Oh, haha, indeed. This thing, so what David has said is, what's the point of this swapping here if we know that X is fresh for A and B? Well, no, do we? Because X, remember, is a atom and a label, and that label could still contain A and B. What gets bound is the atomic identifier associated to X in the body. I'll write it here. Abs XY is bind the ID in X in the body of Y. The ID in X is not bound in the label of X. Does that answer your question, David? Yeah, my head hurts too. Dehydration, you should drink. But I am just about, you're a good audience because you're asking the questions just before I can answer them. Check this out here. So I'm going to create a name NA primed is equal to NA with label A primed. So here's NA and here's NA primed. Okay, David, how are you feeling? Give me a smiley face or a as appropriate. Good, thank you. Now, anytime you feel unhappy, change that emoji, okay? And I'll give myself NB primed is equal to NB with label. So with label is just a little function which changes the label on a name. Now, there you are. So NB primed displays just like NB, but with a different label. Now, is NA equal to NA primed? David, put your hand up, please. I'm not picking on you. Actually, everybody, put up your hand, please, if you think this should be this should return true. Yeah, you're dead right, because we compare on the ID, right? Hands down, please. And let's do this with NB. Yeah, that's also true. And therefore, it stands to reason that abs NA should be equal to abs NA primed NA primed, because after all, we have established that NA is equal to NA primed and NB is equal to N pre-prime. So this should return true. And it doesn't, because abstractions notice the labels on the abstracted atom, on the abstracted name. Yeah? This is what abst really is. It's actually abst primed. I will explain. I'm doing so now. So abst primed takes a label, my label, and an atom, A, and a body, MA, and returns an abstraction. That's what abst is. So what abst does is, Abst actually strips the label from this thing and puts it into the abstraction. So this is where all of the design compromises that I have made come together to create something counterintuitive. I'm not saying this to undermine myself, I'm saying it so you understand what's going on. If this worries you, then use abst prime instead, which will not display that behavior. So just to sum up, there's a design tension between wanting labels or names to not count for equality, but also wanting to use them usefully when you write programs, and it shows up here. Any questions on that before I carry on? Okay. Yes, Ohad.
So it feels like names are really referentials now. And so you've turned Haskell into a very impure language, which is fine by me, but might not be fine by other people. Am I overly worried here?
You are overly worried, but I completely and totally understand where you coming from on this. And indeed, it's all coming from the fact that I can create everything I've shown you so far, and I'm about to change that. Everything I've shown you so far depends on an unsafe perform IO, which is hidden in fresh atom IO. So I'm trying to, I'll just say this, and then I really need, I have prepared you all mentally to see nom. Oh, okay, well, it'll turn up. Nom is where it's at. Let me just check if I have res. Yes, I do. Okay, so this is what everybody's asking for, and everything so far, in a sense, is psychological preparation to understand what this thing is. But I will say, when programming with names, there's always there's a tension between wanting to use the names in a pure sense, in which case freshness is monadic, and wanting to use names as data, in which case freshness is stateful. And I created this package in an attempt to accommodate both methods of programming. I've started with the stateful flavored one, which is actually fine if I'm in the interactive prompt, because I have state. Every time I press enter, I move into a new state. So we're actually okay. But I will now start to show you the monadic styles. And in my experience, it's a mistake to say that one is right and the other is wrong, that the literature is full. My own experiences are full of trying to do it one way or the other. I'm going to make the claim, you need both. You need to have monads around that let you generate fresh names safely, but you also need to, in certain circumstances, throw names around like data. And that will look vaguely impure in certain circumstances. Does that answer your question, Ohad? I'll take that because
yes.
Okay, marvelous. Thank you. Great question. So I am sneaking up. I am sneaking up on nom, but there's a little bit of stuff that I need to, still more ground to prepare. Let us look at this function here. In a sense, this is addressing exactly what you just asked. So I'm going to deliberately play with scope here. So this is a we function which takes in a name and returns two local scopes. Hands up if you can see that. Perfect, thank you. Hands down, please. Hands up if you have any questions about this function before I move on. Perfect, thank you. Okay, so now I'm going to take this function and apply it to a name. So recall that MA it's basically just identical to the atom A, but just because of the way I set up the typings on abstractions, I need to abstract by a name and not on an atom. But when there's no label on MA, it's just unit. Oh, what did I do wrong? It's interesting, it worked before. Huh, Okay, fine. So look at this. This is quite interesting. Can you see that 14 is not equal to 16? So we see here that from a single name, from a single identifier, we have created two distinct scopes. Any questions on that? Okay, I'll carry on. Now let's look at this thing here. Seem to be full of parsers. Oh, I see. Oh, well, never mind. I'll just apply this whole thing. That's just that the type checker doesn't like it, but when it gets the argument, it'll be happy. There we are. So here we have this. Recall, this is MA, this is MB. So we took a name here, we created two local scopes from that single name. This is, I don't quite know how to describe it, dynamic, right? You might call this dynamically, we've dynamically bound the name. And now using concretion, we have concreted these two scopes at two distinct names. So we started off with one name and we have created two. This encapsulates a style of programming that I wanted to make possible. We see the name here is quite free. It gets bound twice, and then these local scopes get unbound in two different name contexts, so to speak. Hands up if I can carry on. Perfect, thank you very much. Okay, hands down, please. Oh, David, thank you so much. David Richter, no, you didn't. Go ahead, Hussein, question?
Well, why did you want to do this? Why did you want to have this style of programming?
Well, this is what we do when names with data. With data, we pass it around our functions. So if we buy into names are data, then we ask, what operations do we have on this data? And these are swapping and binding. So here are the swapping and binding operations. There's something of type, one of these types, and there's something of this type. And of course, there's also conc. These are the basic operations, and so I'm just using them. I'm just programming on names as data in this particular program. Does that answer your question?
Well, I'm not sure, because the line that you have just highlighted on its right branch after the leftmost arrow is producing two contexts. No, the other one.
This one here.
Yeah, it's producing two contexts.
Two local contexts, yes.
And then you are somehow, if I'm not sure if this is the right piece of terminology, but I think you unified them afterwards. And the question is, why do you?
There's no unification. This is a function here that takes two abstractions. It concretes the first abstraction at MA and the second abstraction at MB.
Okay.
I'm going to move on.
Okay.
Fine. If you want to see this, anybody who wants to see this style of programming should look at the systemf file. It's full of this kind of thing. And it leads, I have to say, to a very natural style of programming, because the names are data and we just push the data around. Now, we have seen the type atom. There you are. But actually, if we look up what atom is, atom is equal to k atom of Tom. Right? And I can create atoms of other types. Let's just see if I give any, did I prepare any examples? No, I didn't. Oh, yes, I did. Here we are. Perfect. Okay, so I wanted to give facilities to have, dare I say it, atoms of different types or kinds or sorts or whatever. Again, you'll see this in the systemf file, where, well, never mind. And I also wanted names of different species, let's call them. So if we look up what a name is a k-name of a Tom, and this is just a reparameter so that I can have different species of atoms and names floating around. So I'll give you an example here. This thing here. So now I'm creating an atom, and it's an atom of species int. And here the integer is just used as a type label, as a type parameter. This has nothing to do with numbers. The only thing about Ka is that it's different from A. Any questions on that? Okay, I'll take that to... if you have a question, put up your hand, please. Yeah, it's phantom. That's a nice way of putting it. Except it does make a difference. For example, if I ask whether Ka is equal to A, yes, I should have done this. I do it down here, don't I? Perfect. So let's just, right. So I'm giving myself, so let's just look at the types here. We have two int K atoms, and I can ask if they're equal, and I'll get false because they were generated fresh separately. But if I ask whether Ka is equal to A, I'll get a type error because Tom doesn't match with int. So supposing you have some kind of syntax and you want maybe type variables and term variables, then you're supposed to model these using K-atom Tom, maybe K-atom unit and K-atom string, or whatever. You can create your own types just for the purposes of labeling these atoms. We don't use the inhabitants of the types. We just use them to get some static type checking back into keeping atoms apart. This is actually surprisingly useful. Any questions on that? Okay, a warning, users hate this. Every time I show this package to somebody, they say, I don't like having multiple species of atoms. So this is apparently really confusing. I'm really sorry about that, and I hope this explanation will help. I think it's necessary in the longer term. If there are no further questions on... yes, okay, let's do some names as well. Tom. Tom is a pun. So thank you for asking. Thank you very much. You see, A is a Tom, which makes atom. Tom is a type that I created purely for the purposes of creating a Tom. Does that answer your question? Thank you. Yes, exactly. Thank you for the appreciation. I will now, what have I done? I have Ka, I do. Okay, fine. Oh, did I forget to create NB primed? Okay. Well, never mind. Let's just look at NKA. So this is, thank you very much. I will create KB, which I forgot. Fine. Thank you. I'll run this one again. I get the impression that everyone's totally got this. Oh, I need KB primed as well. Solid. I don't. I can tell that you've all got the idea here. So here we have this name here, and if we look at its type, you can see that NKA has type kname int, whereas NA has type kname Tom. So if you look at something, if you look at the type of NKA, this is an int atom labeled with a T. Whereas NA is a Tom labeled with a string. A Tom atom labeled with a string. I'm being sarcastic here. What could be confusing about this? So I'm really sorry, but that's just the way it's set up. Okay, hands up if I can carry on. Okay, hands down, please. Hands up if there's something that's bugging you and you'd like to discuss it before I move on to the next segment. Okay, Nathan, please fire away.
Can you hear me?
Yeah, perfectly. Thank you.
Sweet. When would you want an atom of a different kind, species, sort than Tom?
Great question. So a very simple answer. If you think about system F, this has two species of identifier, one for term variables and one for type variables. If you also think of Maribel's lectures where she discussed nominal rewriting, there were actually two distinct kinds of name-like entity floating around. There were the so-called atoms, but there were also unknowns. So if you were to model nominal unknowns in the nominal data types package, which I believe is possible, eminently possible, you definitely want two distinct atomic IDs, one to label the unknowns and one to label the atoms. Does that answer your question?
Perfectly, thanks.
Okay, good, thank you. Yes, I agree. So Alexander said he understands the difference between the different species of atoms. He just needs to see examples. So again, System F is a really good place where that comes across. Nominal unknowns is another. If you think about the pi calculus even, you might have variables ranging over processes and variables ranging over channels. And this is very common. Hussein, can you ask me the question offline during a 5-minute break, please? We'll take a wee comfort break. Okay, so I'm going to switch my microphone off for a second, and I'll be back in a few seconds. Thank you. We will now continue. So I believe I've done all of this setup. Oh, I'm building I'd forgotten about this bit. Oh, this is fun. Okay, fine. So I'm still, to my horror, I still haven't told you about nom, but I'm going to follow the script. So we're going to do this. Let's actually write a program. And now that I have cut and paste, this should work. I do recall I imported all of this. I will just make sure that my environment has not been corrupted. Okay, looking good. Here we go. Bang. There we are. I guess I'm not giving away any secrets when I say that this is a data type of the untyped lambda calculus. And indeed, there is an example in the package of precisely this. So this is a simplified version of an example that is in the GitHub repo. So let's just read through this. var takes a name and returns a term. Application takes two terms and returns a term. And abstraction, lambda, sorry, takes a name abstraction of a term and returns a term. Hands up if you think you get that. Excellent. Okay, I'm just being super cautious here. Are there any questions before I move on? Okay. The content of lam, it's not quite that it takes an abstraction. What makes this meaningful for lambda is the machine that it plugs into. So any swappings or any other name-related functions that encounter this will know exactly what to do because it is of abstraction type. So I'll say this again in a different way. So the question is, why does var have type name unit to lambda term and not name int? Just because I set things up like that there. I could have put name int here, but I'm not interested in labeling my my names in this simple example. Name string would have been a better choice. Yes, exactly. It's untyped. So in a simply, exactly. Thank you, guys. You've reconstructed it. Exactly. In a simply typed lambda calculus, these labels here would be the simple types, possibly with a display name as well. Thank you. Spot on. Indeed, exactly. So again, a more conscientious way of setting this up would have been to set up a type called variables and then use that type here and here using a new type declaration. And that is indeed what the theory file does, right? So the question, the point was that I've highlighted here has to match up with that. Absolutely. Great questions. Now I'm just going to give myself some variables. So these are terms. Right, so this is a list of lambda terms. I've just wrapped my names, MA, MB, and MC, in a var wrapper to inject them into the data type of terms. So far, so good. And now I'm just going to give myself a very simple little function. So lam takes a lambda term and returns a lambda term. And in case that the first argument is a variable, it will... Can anyone else hear any buzzing? Hands up if you hear buzzing. Okay, it's just you. Okay. Sorry, I can't help. So you can all read the Haskell, so I'll just put it in. Whoops, that was not intended. Try that again. Copy. There we are. Paste. So pattern matches are non-exhaustive, but I don't care. Any questions on this function before I continue? Okay, so here we are. So let's recall what VA is. And we can see the binding doing its wee magic here. This 20 has turned into a 24. Lam VB, VB, lam VC, VC. I'll try lam VA, VA equals lam VB, VB. I reckon that should return true. Phew, it does. Good. And it should also be, but this should return false. Yes. Okay. Now, actually, harmless as it looks, something quite sophisticated is going on here. And it's hidden here, right? Because you see that wee thing there? Hands up who can see those two letters there. Yeah. Okay, so you can see it. EQ is the generic equality, and I wrote a generic equality instance for abstraction. So when I call here, when I ask the system, is this left-hand side equal to this right-hand side, the system goes, sure, I can check that. So it looks at the top-level term former, the top-level constructor, and find that it's a lam. And underneath the lam, there's an abstraction. and then my little machine from the nominal data types package gets invoked. And Haskell asks that machine, could you please check whether these two abstractions are equal? So the machine does all of its swappings and generating fresh names and stuff, and it instantiates VA to a fresh name and VC to a fresh name, and then checks whether the fresh name on the left is equal to VB, and of course it isn't, so it returns false. Hands up if you get that. Perfect. Thank you. Okay, hands down, please. And this is happening all over here. All of this stuff here, in a sense, this is what one looks at, but all of the hard work is happening here. This is where the machinery is. Okay, and let's use the machinery a bit more. I'll just try to swap MA and MB. I've done a capital N because I'm using the name variant, but all swap N does is throw away the useless unit labels on MA and MB and swap their identifiers in lam VA VA. Well, yeah, okay. And is this equal to lam VB VB? Yes, it is. Fine so far. And again, a little bit of magic is happening here because swap is connected to an engine that knows exactly what to do generically. So all of that stuff that you might have to write, going through the data type and implementing all kinds of bullshit stuff, is just happening in the background. It's all hidden back here. And there's actually, just as an expositor, there's a design trade-off here because I want to hide the complicated bits because they're uniform. That's really important. All of the complexities hidden in here are completely uniform and can therefore be handled by machine, and we want to hide them. But this can also, on some occasion, make it hard to see where the flow. Yes, GHC generics are powerful, but they can obscure flow of control. So that's just a note. It's another one of these design tensions which comes up. And I'll just try something that we know is, let's try that. Hands up if you think this should return true. Hands up if you think it should return false. Who thinks it should return false? Who doesn't know? Hands up if you just don't know yet. Yeah, okay. Well, let's see if we can work it out. Guillaume, I'll come to your question in a second. So we're swapping MA and MB in this. So let's actually just do a rewrite. This VA turns into a VB, and this VB turns into a VA. So I think this should return true. And it does. But also, if I do this, also true. Hands up if you're okay with that. Okay. Thank you. Now, hands up, please. Put your hands down. Hands up, please, if I can continue to the next point. Hands down, please. Hands up if there's something you'd like me to explain further. Perfect. Thank you. So there was a question, what is GHC generics? I can feel it, even just sitting in this room. Half of you already know this, maybe the other half don't. So generics is a machine that you can program to act in some automatic way depending on the structure of the of the type argument. So equality, for example, when it's asked if xy is equal to, okay, maybe I've missed the point of the question. I'll just finish this sentence and then carry on. So there's a little generic machine here that will automatically convert this into x equals x primed and y equals y primed. And my point earlier was that I wrote a little machine to do that for abstraction. I will move on. Oh, I'm definitely having fun here. So this should return true. Hands up if you think this should return true, please. Let's find out. Yes, it does. And it's actually easy to see because the VA here has got bound, and so this V can alpha convert into a VA. It's completely standard. This one here, let's just try to read it. Yes, I agree, Ohad. Thank you. We have a VB here. We have a VA. You know what? Maybe it's just the lecturing, but I have no idea whether this will return true or false. And I don't need to care because I can just ask the machine, right? I trust it enough that it will do these calculations for me. There you are. Now let's look at this. So this is a function called fun, and it abstracts MA in lam_va, and I'll just I'll iter expand that. There. I'll call this T because it's an untyped lambda term. Now what's significant about this is we're abstracting a name in a function. So we see here we're abstracting names in terms, fine, but here we're abstracting the name in a function, and the package is absolutely fine with it. It doesn't care. So let's try to run this. I reckon this should return true, right? Because we concrete MA at MB, so this will return lam VB. Yes. Hands up if you have any questions about. Hands up if this makes sense. Interesting. Hands down, please. Yeah, Ohad has found a good emoji. Hands up if it doesn't make sense. Okay. Okay, Swaraj, can you put words to where the confusion is? What's not to understand, please?
Hi, can you hear me?
I can perfectly, thank you.
My question was in fun, you abstract MA, but then you concrete it with
MB.
Maybe I should just work this through actually.
Sure.
Yeah, sorry. Actually, I'll just work this through. I'll ask on Slack.
That's fine. I'm glad you spoke up. This, you see, now we're going out of. Please switch your microphone off. Thank you. Let's do. Where was I? I was here. Let's do this. Whoops. Okay. So here we're concreting fun back at MA. So this will be lam VA. So this is lam VA VB, which should not be equal to lam VA VB. Sorry, it should be equal to lam VA VB. That's right. Okay. Yeah. So that works. So I think of this as a function, you see, and this function here has non-trivial support in the nominal set sense. It depends on the name A, and we are completely at liberty to locally bind that name in an abstraction scope, which we can then concrete later. So this is a function. We're really seeing the dynamic binding going on here. We're taking this function and we are dynamically binding the name A in this function, and the system is completely fine with that. The technical reason this can be done is that swappings distribute through functions. So anything you can swap through, you can abstract in. And because you can swap through anything, you can abstract in anything. Hands up if I can continue. Perfect. Thank you. Okay, so now I'm going to write a substitution function. So first of all, I'm telling you, I was up late last night finding all of the language flags I needed to switch on to make this thing work. There we are. I'm just making a little point with this function here. There is a background substitution engine in the nominal data types package. So it's a type class, and this type class has certain generic properties that make it just work, and we just need to plug this sub engine into the untyped lambda calculus data type. And the way we're going to do it is just the way things are set up. We just need to provide a function that will input an untyped lambda term and either output a substitution on it or output nothing. So we only substitute on variables. The generic engine will take care of everything else. So this nothing here says treat everything else generically. So substitution will distribute through abstraction and I'll just put this thing here so we can see it. The substitution engine will go straight through application and hit its 2 arguments. It'll go straight through lam. It knows what sub knows what to do with abstraction, so it'll go through in a capture avoiding manner and hit the UL here. We just want to trap the vars and do the substitution, right? So sub VT is a function that will take a term and return a term. It acts generically on most things, but will substitute V prime. It will substitute V for T. Hands up if that kind of made sense. Good, thank you for that. This is another exercise, well, another example. This is another example in the examples folder, so you can see all of this in the untyped lambda. There I now have sub. There you are. So this is a generic version, but now UL is an instance of sub, so I can substitute MA for VB in lam VB at VB VA. One second, I'll come to that. And let's just sanity check this. It's not very readable, I acknowledge, but this VA should have turned into a VB. So we just need to know the number of VB, which is indeed 21. So that is that. Okay. So this has worked. And I think this is a particularly, it's just very compact. Once you have the machinery set up, everything's working auto-magically. You just need to tell sub that this is, you consider this to be the variables in your data type. Okay, Ohad asked about simultaneous substitution. Sure, if you want a simultaneous substitution, you just take a function from names to terms and trap every var and apply the function. That's how you do it, and that would work perfectly well. Good, thank you, Ohad. Okay, so just to sum this example up here, once we're in this framework, this does a hell of a lot, and we can write standard functions with, I think, very appealing compactness, and leave the generics to handle everything else. And now, finally, in the last half hour, I can tell you about NOM. Who would like to talk about NOM? Hands up, please. Thank you. I'll take that as a yes. I'm just going to eat a jelly bean. These things are good. I'm just reloading my environment. Oh, don't know why that happened. Let's try again. Yeah. Okay, so atom list, name list, complex name list. Yeah, that's fine. I missed any comments, so if there's something you want... Oh, do you have a question? Okay, you don't have a question, so no problem. No. Let's look. Abs, MA, MA is equal to abst, MA, MA. Now, I've abstracted a name in a name. Now, abst is functorial. I'll ask the question, what can we do with this? So once we've abstracted a name in a name, what can we do? Well, there is a functorial action built into this. So this will go under the binding and put the body of the abstraction in a singleton list container. Okay, so that's quite nice. And we can exit from abstractions. I can take this, and I mean, it's an abstraction, right? So I can concrete it. I can concrete it at MB if I want to, or MC. So this is MC, and it's in a singleton list container. Let's just check the numbers. Yep, we're good. And in one way or another, you guys have given me no peace over the fact that this is not terribly idiomatic. It feels stateful, this concretion. So we can sum this up as a question, where's the monad? That is, supposing, ladies and gentlemen, supposing we don't want our names to be parading around naked inside our program. Suppose we are modest Haskell programmers and we want to keep our names under control. So it is for this that res and nom were created. So res takes a list of atoms and a body and returns a thing called knom SA. Let's just compare with abst. Now, the justification is a little bit off, but just to spell this out, this corresponds to one of these. And here we're abstracting, with abst we abstract by a name, here we abstract by an atom. That's a non-essential difference. It's just that empirically, when we're abstracting, we tend to be abstracting over a atom labeled with semantic information, but when we're restricting, the more common cases we have a single atom. We have a body here, and here we have a knom, here we have a kabs. So let's just compare them. I'm going to restrict A and B in AC, just because I can. And let's just look at AC. So this is the C here, and this is A, but it's got restricted here, and this is the restricted B, which isn't used in the body, but is floating around in the restriction anyway. Okay? Any questions on this before I move on? Cool. Thank you very much for the smiley, David. Please feel free to use emoji, and any feedback helps. Now, most things norm-related, I'm just going to dump this, are in the norm-theory file. So all of this stuff, I'm waving my hand around, all of this stuff is in norm. This is a function we'll be most interested in. So res, I'll just do a few to give you a flavor. We've restricted here, we've restricted B in AB. We can do the same thing with abstraction. So they look quite similar in this respect. Right, they do look quite similar. And res can also restrict on, 1 second please, I'll just see if it's important, apologies. Right, sorry about that. You can restrict by names, and all restriction by a name does is throw the label away. So this should be equal to res b ab. Oh, what did I do? Oh, yes, of course, I know what I did. Oh, yeah. Yes, I'll come back to that. That's my next point. Okay, hands up if you're with me so far. Don't worry, David, I'm going to explain. Cool, thank you. Okay, so check this out. Now let's go real slow and understand every step of this. So here we are functorially going underneath this abstraction and putting this pair in a singleton list. Fine. Let's try the same thing with res. Res is a functor too. Fine. Now let's try to treat this as a monad. So here we're creating a restriction, and then we're feeding this into a function which adds a restriction by MB to the binding context. So I would read this as restrict MB under this binding. Okay? Can you give me a smiley face if you're cool with this so far, please? That's looking good, thank you. I'll press enter. Wow, this is so amazingly cool. Look, can you see here that this 64 has been bound and turned into an 87? That is so cool. Hands up if you think that's cool. Thank you. And you've got to agree, this is cool. Okay? Now we're going to try the same thing with abst. And this will return a type error. And the reason is that abst doesn't have a monad instance, only res does. Is this essential? Actually, no. All it's coming from is the fact that abst binds by an abstraction is an abstraction by a single name, whereas a restriction, an OM here, this is a restriction by a list of names. So it's easy to add bound names to the binding environment in an OM. We can't do that in an abst because we're only binding by a single argument. It would be perfectly possible to create another version of abst that binds by a list of names. And I'm not going to go there. There are reasons why I didn't do that, but they're not really mathematical. They're programmatic. But this is where the real difference is. So, oh, I do apologize. The term was malformed. Ah, I see. Yes, of course. Thank you. Thank you. Okay, I'll do that. Thank you very much. I apologize. I will fix that right now. You're absolutely right. Now, there's a question. Does the list order matter? David, for what? For what would the list, for anything? Well, watch this, and this will hopefully answer part of your question, or ask me again in a minute. So let's try to restrict A in A and ask if this is the same as, in fact, restrict B in B. Now, the answer is no, whereas if I abstract A in A, it should be equal to abstract B in B. That's true. But it gets worse, much worse. Hands up who thinks this should return true. Hands up who thinks this should return false. Now, there was an ambiguity. Thank you. There was an ambiguity in my question because I didn't specify whether should is in a moral sense or in a predictive sense. So it returns false. Now I'll ask again, hands up who thinks this should return true. Oh, you bunch of fanatics, you. Hands up who thinks this should return false. Oh, okay, well, I think it should return false because, wait, I can explain. The equality here is monadic, right? I did say res was a monad, so this is actually equals being fed two arguments. And what happens when you have two arguments? Well, darlings, what you have to do is look into this argument, and when we do this, a fresh name is created, and I might as well use A. And when we look in this argument here, well, a fresh name is created for the body, and we get that. That's why it returns false. It's different with abstraction, because with abstraction, we haven't abstracted by a list, you see. We've abstracted by a single name. So here, yes, we can go underneath, we can go into this abstraction, but it makes sense to concrete the abstraction, the two abstractions at the same name, the same fresh name, because it's pointed, right, in a way that res is not. Res takes a list, a restriction is a list, ABC, like that. So there's no distinguished atom here. Yes, absolutely. Happy to do so. But that's not quite as, you'll get the same behavior with abs just because the show instance generates a fresh binding in each time. Thank you. Okay, so here, abs and res really do differ, and you heard me perfectly well the first time, but I'll say it again. Here, the equality instance concretes both sides at a single fresh atom. Here, the equality instance just acts blindly on the monad. It goes underneath the first binding and underneath the second binding, and then compares the resulting bodies. Right, now, you might say, okay, that's all very well, but there is a sense in which they should be equal, and there is a machine to do just that for you, and it's in the file unify. I'll just show it to you. It's, where's it gone? Unify. So this file here contains a machine specifically to handle a case where you want to sensibly unify bindings in restrictions. So There you are. So this is the true that you were looking for when I asked whether res A was equal to res B. Now that's false because A is not equal to B. This is true because there is a permutation acting on the bound atoms on the left that will make the body equal to a permutation acting on the bound atoms on the right. Any questions so far? Hands up if I can proceed. Perfect, thank you. And just now, this is really useful. This machinery, this stuff really gets used. I didn't create it just for my satisfaction. I created it because I needed both, right? I'm just going to draw you a little picture. So here I have some stuff. And here I have another container with some more stuff. And when I put them together, and both of these have some bindings, right? Now I'm going to put them together. Watch this. Bang, now they're together. Now, question. Do I want the local bindings to, in some sense, be identified, or do I want them to accumulate? And the answer is it depends. Sometimes we want one, sometimes we want the other. So here, by default, the local bindings accumulate. They do not identify. If you want them to try to be identifiable, then we use this function here. Let's run through a few examples. There's this function, unify perm AA. There you see. So this will actually return the unifier. And yes, these are identifiable. This is identifiable. This is identifiable. That's identifiable. I'll just give one more. Right, I reckon that should return nothing because there's no permutation that can make ABA be equal to BAA, right? There you are. Okay, so this is the engine. This is the engine that powers equality on res. This is an interesting example. The engine knows what to do on abstractions. Actually, hang on a second. Look at this. So this says we map 63 to 64 and 64 to 63, but here we just map 64 to 63. So because this name A is bound, the way unify perm works is it will first try to unify these two bodies, and then it will delete any bound atoms from its final result there. I hope that's clear. Any questions before I move on to this example here? Okay, hands up if I can carry on. Marvelous, thank you. Before I forget, I'll just mention, if you want to see this machinery really used properly, then look in the idealized EUTXO file. This is where it gets used. Oh, okay, I'll wrap up in a second. Thank you very much, Ohad. Now, this is a set. In fact, I'll make it even simpler. So now we're trying to unify a set AB with a set AB, and we get a type error. Oh, but I've forgotten to import. Can I just have a minute to finish this off, Ohad, please? Oh, interesting. There, that should do it. There we are. So there's no instance of unification on sets. Now, this is just for experts here. Why not? So the unified perm machinery is very, very specific. It will unify things that are completely structured such that if a unifier exists, then there is precisely one such unifier, up to ignoring irrelevant atoms. Now with sets, and this is the same issue that Maribel, she mentioned it too, with sets, there's more than one possible unifier. We could map A to A and B to B, but we could also map A to B and B to A to unify these two sets. So purely for program, and also the number of solutions will increase as factorially in the length of the lists. I didn't want to go there, so I did not build that machinery. It could be built, I just didn't do it. In practice, for the idealized EUT example is completely structured as lists naturally. So if a unifier exists, it's unique. I can imagine in other situations we might want something more powerful, but that would require a step increase in the complexity of the algorithm. So I just didn't program it in. Okay, natural place to stop. Thank you very much. Any final questions? Oh, okay. List. Thank you for asking for the notes. I'm planning to flesh it out to something a bit more substantial. David, what was your question again? Let's see, I'll need to go into the chat. Does the order in res list matter at all? Right, so that was the original question. Let's find out. Let's find out. So it doesn't matter here, but because it's always going to return false, right? Well, not always. If I give it 1, then this should work. But only because this is a nameless type. But let's try it with unify. So let's try to unify res ABA with res BAA. Hands up who thinks this should return true. Hands up who thinks it should return false. Interesting. Okay, let's try it. It returns true. So the way the engine works is that basically A can go to B, and we're allowed to permute any names that are restricted. That's the thing. So I'll just show you. This will return false because we can't move C, right? Because C is not restricted. Oh, unifiable. My apologies. Yes, okay. My mistake there. Let's try this. There. You see that even that returns true. And my previous example, what I should have done was this. That should return false. Oh, I didn't unify integers. Well, it would return false if I'd done the engine for integers. Interesting. Okay. Any other questions? Okay, thank you very much. Handing you back to Ohad.